Alright, in this video we're going to finish up our section on the shape of a graph by looking at a couple of examples of trying to use first and second derivatives to tell us where a function is increasing and decreasing and where it is concave up and concave down. So let's look at the function f of x is equal to x to the fourth minus 4x cubed. We're going to try and determine first the increasing and decreasing intervals because we know that we just need the first derivatives for those, right? So increasing and decreasing intervals, we want to look for where the first derivative is positive or negative. So let's start there. So the first derivative of this function is going to be 4x cubed minus 12x squared. Now keep in mind, f is a polynomial, which means it's defined everywhere, and its first derivative is going to be defined everywhere, its second derivative is going to be defined everywhere. We don't really have to worry about any place where the derivative is undefined, or even where the original function is undefined. So we're just going to set this equal to 0 to look for those critical points, those places where the first derivative is equal to 0. Alright, how do I solve something like this? Well, I've got factors of x in both of these terms. In fact, I also have a factor of 4 in both of these terms. So the largest thing I can factor out would be 4x squared. And I'm left with x minus 3 on the inside. Setting each one of these factors equal to 0 is going to give me, if 4x squared is equal to 0, that would mean x is equal to 0. And if x minus 3 equals 0, then that means x is equal to 3. So these are my only critical points. And those critical points may or may not be relative or local maxes or mins, but we need to figure out the increasing and decreasing intervals before we can determine whether they're maxes or mins. Alright, so let's do just that. We're going to break up our number line, put 0 and 3. So our intervals here would be negative infinity to 0, 0 to 3, and 3 to infinity. And to determine where f is increasing and decreasing, we need to determine where f prime is positive or negative, right? So I'm going to plug in a point from each interval into f prime. So let's start with f prime of negative 1. I'm going to plug it into the factored version because it'll be easier to determine whether this is positive or negative. So when I plug this in, I get 4 times a negative number squared times negative 1 minus 3, which is negative. So this is going to be 4 times a positive times a negative. So overall, this is going to be negative. Now that tells me that my original function f is increasing on this first interval. Now I repeat this step with the interval from 0 to 3. Choose a point in that interval like 1. Plug it into the first derivative function, and we'll get 4 times 1 squared, that's a positive squared, times 1 minus 3, which is negative. So this is going to be 4 times a positive times a negative. So this is also going to be negative. Oh, what have I done here? When f prime is negative, that means f is decreasing, not increasing. Like I said, my brain is melting because of this quarantine. Decreasing. Alright, when we plugged in 1, we still got a negative number, which means f is still going to be decreasing on the second interval. Right, that's fine. It just means that this critical point didn't happen to be a max or a min. That's allowed. But when I plug in something in this last interval, like when I plug in, let's say, 5 into the first derivative function, I'll get 4 times something positive squared times 5 minus 3, which is positive. So now I get something positive overall, which means my original function is increasing, right? When the derivative's positive, the original function is increasing. Oof, okay, cool. So now I know where my increasing and decreasing intervals are. F is going to be increasing at, on the interval 3 to infinity, and decreasing on those first two intervals, so we could sort of put these together into one big interval and say negative infinity to 3. And we have one local minimum when we switch from decreasing to increasing. So at f of 3, right? Local maxes and mins are outputs. So f of 3, so when I plug that in here, we get 3 to the 4th power minus 4 times 3 cubed, which is going to be negative 27, I think. Okay, so that's the first part, right? We use the first derivative to determine local maxes and mins and to determine increasing and decreasing intervals, but we still have to go back and figure out where f is concave up or down. We follow really similar steps here, but we do them with the second derivative. So look for where f double prime of x is positive or negative. So let's repeat these same steps, but looking at f double prime. So the second derivative of x is the derivative of f prime, right? F prime was 4x cubed minus 12x squared. So the derivative of that would be 12x squared minus 24x. Again, this is defined everywhere, so I just need to set it equal to 0 and solve. I can factor out a 12 from both of these, and I can factor out an x. So this is 12x times x minus 2. Setting each one of these factors equal to 0, I get possible inflection points at x equals 0 and at x equals 2. Now remember, we don't know if these are actual inflection points yet. To determine whether they're actual inflection points, we need to see if the function changes concavity here. So we're going to do the same thing we did before. We're going to set up a number line, put our potential inflection points 0 and 2 on that number line, and break it up into intervals from negative infinity to 0, 0 to 2, 2 to infinity. And we're going to test a point in each interval by plugging it into the second derivative function using the factored version to figure out whether that output's positive or negative, which will tell us where your original function is concave up or concave down. So let's plug in something like negative 1 into the second derivative function. We'll get 12 times negative 1, which is negative, times negative 1 minus 2, which is negative, and the negative times the negative is positive. Okay, that tells us that our original function f is going to be concave up on this first interval, right? Positive means concave up. Now let's plug in something between 0 and 2 into the second derivative function. If I plug in, let's say x equals 1, I'm going to get 12 times 1 is positive, but 1 minus 2 is negative. Positive times a negative is negative overall, so f is going to be concave down on the second interval. And finally, f double prime of, let's say, 3, which is in this last interval, is going to give us 12 times 3 is positive, and 3 minus 2 is positive. A positive times a positive is positive. So we're concave up on this last interval. This is determining that both of these points, both of these x values, are x values of inflection points because the function does change from concave up to concave down and then down to up at those points. So we have our concavity. The function is concave up on negative infinity to 0, union 2 to infinity, and f is concave down from 0 to 2. Great, and our inflection points, remember inflection points are both x values and y values, inputs and outputs. So we have inflection points at 0, comma something, and at 2, comma something. And to figure out what those outputs are, we have to actually plug 0 and 2 into the original function. The original function, of course, is what we had up here, x to the 4th minus 4x cubed. So when I plug in 0, I get an output of 0, and when I plug in 2, I get, let's see this? Okay, when I plug in 2, I get f of 2 is 2 to the 4th minus 4 times 2 cubed. So 16 minus 4 times 8 is 32, so this is negative 16. Okay, So that's that example. With polynomials, it's pretty straightforward. We don't have to deal with anything funny going on like holes or asymptotes. But we do have to be a little bit more careful on problems like that. So let's do one example where the function's a little bit more complicated. We're going to do the same thing here where we try to figure out critical points, inflection points, and intervals of increasing and decreasing in concavity based on this particular function here. Now I've gone ahead and actually found f prime of x and f double prime of x for you and even simplified them so it's a little bit easier to determine where those critical points and possible inflection points would be. But maybe it's worth pointing out right from the start, this function here, f of x, right? This function is going to be undefined at x equals 1 and at x equals negative 1. Right, at x equals 1 and negative 1, we have that f is undefined. So those couldn't really be critical points or inflection points. However, the function could still change from increasing to decreasing, or it could change concavity even at those particular x values. If you had something like an asymptote at 1 or at negative 1, you could change from increasing to decreasing right at that asymptote. Okay, so anytime that we're doing these tests, we're going to take those points where the function's undefined, 1 and negative 1 in this case, and put those on our number line when we're breaking up the number line, right? They're not necessarily critical points or inflection points, but we're still going to take them into consideration. All right, so let's do an example here. Or let's start with the increasing and decreasing in the critical points. For these, remember, we have to look at the first derivative. That's this function right here. Okay, so we want to figure out, for critical points, where is that function undefined or equal to 0? So note that for critical points, f prime of x is only going to equal 0 when the numerator of this whole function is equal to 0, right? Fractions only equal 0 when the numerator equals 0. So when 4x is equal to 0, which is when x is equal to 0. So x is your critical point. This function is also going to be undefined at 1 and negative 1, and so we do want to take those into consideration. We just don't really consider them critical points because the original function is not defined there. But we could also change from increasing to decreasing or vice versa at x equals 1 and negative 1. So when we break up our number line, we're going to put 1 and negative 1 on there along with 0. Okay, so this breaks up our real number line from negative infinity to negative 1, negative 1 to 0, 0 to 1, and 1 to infinity. So I'm going to plug in a point in each one of those intervals into the first derivative function, that's this one right here, and just figure out, is it positive or is it negative? All right, so let's say I plugged in negative 2 into the first derivative function. Okay, the numerator is going to be negative. 4 times negative 2 is negative. And the denominator I'll have, look what happens here. The denominator I'm going to have something squared times something else squared. Well, anything squared is positive. Anything squared is positive as long as it's not 0, which it won't be on these intervals. And so the denominator is just always going to be positive for this first derivative function. All right, so a negative divided by a positive is negative, and that tells us that f is going to be decreasing on the first interval. Okay, f double prime of x, if I plugged in, oops, sorry, I did that wrong, single prime, right, we're still on the first derivative test. So we want the first derivative of some x value between negative 1 and 0. So let's find f prime of negative 1/2. Negative 1/2 is in that interval. The numerator is going to be negative, right? 4 times a negative is negative. And the denominator we said was always positive. Anything squared is positive, so these two are both positive. So again, on the second interval, we're still negative, so we're still going to be decreasing. All right, then we hit 0. From 0 to 1, we want to plug in something positive, like 1/2 between 0 and 1. If I plugged in a half, I'll have positive on top, positive on the bottom. So overall, I'm going to be positive on this interval. So f is going to be increasing. And if I plug in something greater than 1 into the first derivative function, I'll get positive over positive again. So overall, I'm positive, or I'm going to be increasing for my original function on that first, and on this last interval. All right, so it turns out at those -1 and +1 values where your original function is undefined, we don't actually change from increasing to decreasing, but we could have, so it's important that we put them on there anyway. All right, now, the only critical point was at 0, and we did indeed change from decreasing to increasing there, so we're going to end up having a local, let's see, if we're going down to up, that's going to be a local min at f of 0. F of 0, of course, if we plug that into our original function, is going to be 1 plus 0 over 1 minus 0, which is 1. And we have that f is increasing on 0 to 1 and 1 to infinity. It's not defined at 1, so we don't want to say just 0 to infinity. But f is decreasing from -infinity to -1 union -1 to 0. Again, it's not defined at -1, so we don't want to include -1 in those intervals. Great. So this is telling us everything we need to know about increasing and decreasing intervals. Next, we move on to concavity, and for that, remember, we have to use the second derivative. Right? Second derivative tells us about concavity and about inflection points. Okay, so just like before, for possible inflection points, we need to see where the second derivative is either undefined or equal to 0. Undefined or equal to 0. Well, it's only going to be equal to 0 when the numerator is equal to 0. So when is -4 times 3x squared plus 1 equal to 0? -4, I mean, we could divide both sides by -4 to get rid of it. 3x squared plus 1 is going to be strictly positive. Right? We're taking something, squaring it, and then adding 1. Right? It doesn't matter that you're multiplying it by 3. Anything squared plus 1 is going to be positive. And so this ends up being never. Right? The numerator is never equal to 0, therefore the second derivative function is never equal to 0. So actually, we don't really have any inflection points here, but it's still possible that you change concavity at those points where the original function is undefined, right? Namely at 1 and -1, we could still change concavity. F could change concavity at 1 or -1. Okay, so we're going to do the same thing here. Break up our number line. 1, -1, and 1. Our intervals would be -infinity to -1, -1 to +1, and then 1 to infinity. And we're going to choose a point in each interval, plug it into the second derivative function all the way up here, and see if the output is positive or negative. Now, keep in mind with this function, when you're plugging things in, no matter what x value you plug in, other than 1 and -1, the numerator is now always going to be a -4 times something positive. A negative times a positive is always negative. So no matter what x we plug in, the numerator is going to be negative. Denominator, maybe not. We'll come back to that, right? But the numerator is always negative. So let's plug in some x values in each interval. If I were to plug in, let's say, -2 into the second derivative function, we said that the numerator is always going to be negative, but the denominator won't be, right? So if I plugged in -2 into the second derivative function, we'll have -2 plus 1 cubed is negative, and -2 minus 1 cubed is also negative, right? So on the denominator here, we've got a negative times a negative. So overall, it's negative over a positive, right? 2 negatives make a positive, which means overall on this first interval, the second derivative is negative. Make sure you can actually see this. Okay. That tells us that the original function f is going to be concave down. on this interval. Okay, now from -1 to +1, we need to plug in something like 0 into the second derivative function. The numerator we said was always negative. The denominator, if I plugged in 0, this will be positive times a negative, right? 1 cubed times -1 cubed. A positive times a negative is going to be negative overall, which means we've got a negative divided by a negative, and that gives you a positive output. So your original function f is going to be concave up on the second interval. And finally, plug in something like, I don't know, 2 into the second derivative for the last interval. The numerator is always going to be negative, but the denominator here is going to be a positive times a positive. So when I plug in 2, I get negative on top, I get positives on the bottom. So overall, I get something negative on this last interval. So f is going to be concave down. Right, remember, there's no inflection points here. -1 and +1 aren't actually inflection points, even though the curve does change concavity there, because the original function is not even defined at -1 and +1. Okay, so we do change concavity, but there's no actual inflection points. And now we can say that f is going to be concave up on this middle interval from -1 to 1, and f is concave down from -infinity to -1, and then from 1 to infinity. Okay, and that's everything that we were looking for in this. But I have a follow-up question, which is, we've got all this information about increasing and decreasing intervals, about concavity of the graph, but what does this graph actually look like? Right? How do we know what this graph really looks like? We know where it's decreasing and increasing, but like that could look like a lot of different things. So if we want to figure out the actual shape of this graph, we really want to know what's going on at those x values where the function is undefined. Do we have holes there, or do we have asymptotes there? Because we know that the function switches concavity at those points, even though the function doesn't switch whether it's increasing or decreasing at those points. Right? So finding out what's happening at x equals 1 and -1 is going to tell us a little bit more about what this graph looks like. So remember, f of x is going to be the function 1 plus x squared over 1 minus x squared. That's the original definition. If we were to plug in 1, on top we'd get 1 plus 1 squared, which is 2, and on the bottom, of course, we'd get 0. If we were to plug in -1, on top we'd get 1 plus -1 squared, which is still going to be 1 plus 1, or 2, and on the bottom we get 0. Now remember, anytime you actually plug in an actual x value and you get non-zero over 0, that tells you something very specific is going on there. In particular, it tells you that you have a vertical asymptote. So we have vertical asymptotes at -1 and +1. And now we have a better idea of what those functions are doing. Now, if we really want to sketch this graph, there's a couple of other things that would be useful here. In particular, it would be useful to know whether you have any horizontal asymptotes. Now we got to think back to chapter 1. How do we know whether a graph has a horizontal asymptote? Horizontal asymptotes have to do with limits at infinity, right? As x goes to positive or negative infinity, what is this function doing? So if we want to know the limit as x goes to positive or negative infinity of this particular function here, 1 plus x squared over 1 minus x squared, plugging in infinities here gives you infinity over infinity, which means we can apply L'Hopital's rule. Putting everything together here, right? Everything from the past 2 months all coming together, and say this is equal to the limit as x goes to either infinity of the derivative of the top over the derivative of the bottom. The derivative of 1 plus x squared is 2x. Derivative of 1 minus x squared is negative 2x. This is still going to be an infinity over infinity L'Hopital's rule. Will still apply. So this is equal to the limit as x goes to either infinity of derivative of 2x is 2, derivative of negative 2x is negative 2, And this is just a constant, and it's equal to -1. So yes, we have a horizontal asymptote at -1. So yes, at y equals -1. All right, this is telling us even more about the graph. Some other things that might be useful is knowing whether this function has any y-intercepts. So does it have any y-intercepts? Well, a y-intercept is going to happen anywhere. How do we figure out y-intercepts again? Well, y-intercepts are where x is equal to something, but y is equal to 0, right? So, oh no, that's x-intercepts. Oh. Y-intercepts would be x is 0. So we plug in 0 into the function, and we get 1 plus 0 over 1 minus 0, which is 1. So we have a y-intercept at 0, 1, and we have an x-intercept wherever the entire function is equal to 0, wherever 1 plus x squared over 1 minus x squared is equal to 0. Well, this is only going to happen when the numerator is equal to 0, but the numerator is never equal to 0. So we have none. We have no x-intercept, right? No zeros or roots here. All right, let's try to put all of this together and sketch some kind of a graph that would make sense for this whole big function. All right, I'm going to start by sketching in those asymptotes and then trying to draw the graph around it. I have vertical asymptotes at 1 and -1. So I'm going to draw those first. I also have a horizontal asymptote we set at -1. And that's for as x goes to positive and negative infinity. Oops, sorry, you can't see that graph. So I'm going to draw this horizontal asymptote at -1. Oh, I've drawn this poorly. Sorry, -1 should be right here. Should actually go through the point. All right. And what else do we have? We have a y-intercept for our graph. We said at 0, 1. Right, 0, 1 is right here, so this is an actual point on our graph. We had that point 0, 1, if you look back on the last sheet, 0, 1 also happened to be a local min of our graph. So it's going to end up looking something like this. All right, we'll come back and finish that up later. But we can try to use the increasing and decreasing parts to sketch the rest of this graph. Right, so from -infinity to -1, the function's decreasing. So I need to sketch it in so that it's decreasing, going downhill from left to right. The only way that it could do that is if it's an asymptote that looks like this. Right, that's the only way it could be decreasing. Okay, similarly, from -1 to 0, the function's still decreasing and still coming downhill. So after that asymptote from the other side, we should still be decreasing, so we should be coming down from positive infinity like this. And I know that eventually I have to hit that point 1 because I've already sketched it in. And then change directions because from 0 to 1, the function's increasing. It's going uphill. It's going to keep doing that as you head towards this next vertical asymptote. And what happens after that? Well, from 1 to infinity, the function is still increasing. So there's no way that I could be coming down from this asymptote on the other side because I need to be increasing, which means I need to be coming from this direction. I need to be increasing forever, so I'm going to head off towards this horizontal asymptote like this. All right, now let's just do a sanity check here and make sure, does this match with our concavity that we had checked? When we did our concavity test, we said that f should be concave down from -infinity to -1. Sure does look like it, right? This looks like it's bending down. This is concave down. Concave up from -1 to +1. Yep, that checks out. And finally, concave down from 1 to infinity. And we see that from 1 to infinity, the curve is indeed bending down. right? So putting together all this information that we've been learning all semester, we finally have a way of graphing a function that right off the bat, we don't really know what this function 1 plus x squared over 1 minus x squared looks like, but now we do. So we'll hopefully do a few more examples on a worksheet and in the homework as well.